Hi everyone! Today, we're going to be introducing a data structure called a linked list. Specifically, we'll be going over 1. What a linked list is, and 2. When it is useful. So what is a linked list? A linked list is a linear data structure in which elements are connected together using pointers. First, let's go over some basic terminology. The head of a linked list is the first node, and the tail is the last node. The tail always points to none. Now, let's build a linked list together. Let's start with building a node class, as nodes are the building blocks of linked lists. Each node in a linked list consists of two things. Number 1, a data element, such as the character A. This data element can be of any data type and is initialized when a node is created. And 2, a pointer to the next node. Initially, this pointer is set to none. Now that we have a node class, let's build a linked list class. We reference a linked list by its head. So let's add a head property to the linked list. Alright, so now we're done building our linked list. An additional note is that some implementations of linked lists do not include an actual linked list class. Rather than tracking the heads explicitly as a property of a linked list class, they just pass around the head node directly. Okay, so now that we've built our node and linked list classes, let's make an instance of a linked list. We're going to be building the linked list depicted on the bottom right, with the nodes A, B, C, and D. The first step is to create instances of all the nodes. Next, we set the pointers of each node to connect the nodes together linearly. Finally, we create the linked list instance with A as the head node. And now we're done building our linked list with nodes A, B, C, and D. Now that we know what a linked list is, when are they useful? Linked lists have constant, or O of 1 time insertions and deletions. To see why, let's pretend we were inserting the element B in the diagram below. Inserting the node B only requires manipulating two pointers, the one before B and the one after B. And deleting the node B only requires manipulating the previous node A's pointer. A caveat with this is that we need to already have the previous node if we want to perform an insertion or deletion in constant time. In contrast, traditional Python lists have linear, or O of n time insertions and deletions. This is because if we were inserting an element with the index of 1, we'd have to increase the indices of the rest of the elements in the list by 1. And if we were to delete an element with the index of 1, we'd have to decrease the indices of the rest of the elements by 1. So, does that mean linked lists are always better? Well, not necessarily. Let's look at another example to see why. Linked lists have linear, or O of n time random access. This is because, in order to visit a random node in a linked list, we must traverse the entire linked list until we get to the element that we want. For example, to access the last node in this linked list, D, we have to traverse the entire linked list through A, B, and C before we finally get to D. However, traditional lists in Python have constant, or O of 1 time random access, since we can immediately index into any position in a traditional list. Alright, that's it for today's video. Here's a summary of everything we've discussed. Hopefully this was helpful for you. And thanks for listening.